been abbreviated at least. So thank you very much for the introduction, and I'd like to thank the organisers for inviting me to speak here. It's a great honour. So I'd like to start by introducing the idea of Euler systems, what they are, and how one goes about studying them, before moving on to this specific new example I want to describe at the end of the talk. So the general setup. I want to consider a p-adic Galois representation V. So V is finite dimensional vector space over QP with a continuous action of the Galois group of Q bar over Q. And I'm going to assume that V is unramified almost everywhere. So, for instance, the Tate module of your favourite elliptic curve, base extended to QP, would be an example. And we want to study the Galois cohomology of such representations. So this is important in all sorts of setups. For instance, most of the results we have towards the Birch-Schunert-Dyer conjecture come from studying the cohomology of the Tate module of your elliptic curve and then locating the points of your elliptic curve inside that. But there are lots of other applications where you might want to study Galois cohomology, for instance, Selmer groups in deformation theory. And yes, they're clearly important objects. So one of the main tools we have for studying these guys is Euler systems. So if V is as above, an Euler system for V it's a collection of cohomology classes in H1 of V, not just over Q, but over all abelian extensions of Q as well, or more or less equivalently, all cyclotomic fields. So for each M, you have a class Zm. And a minor technical point, it lands not just in V, but in some fixed lattice in V independent of M. And these have to satisfy an important property, the norm compatibility relation. So if L is prime, and you take the class over mu ml, and norm it down, take the co-restriction down to Q mu m, then you require that you get one of two things. If L divides M, or if L is a bad prime, then you should just get Zm. So the bad primes you don't really know what to do, so you just do the simplest thing. And when L is a new prime, and it's a good prime for V, you require that you get Zm acted on by an Euler factor. And this Euler factor is a polynomial and a minor point, it's not the Euler factor of V, but the Euler factor of the Tate dual V star 1, which is in many examples the same thing as V, but not always. And sigma L is the image of the Frobenius in the finite group. Galois group of Q mu m over Q, which is well defined because L by assumption doesn't divide M. So that's the definition. It's due in this form, I think, to Carl Rubin, based on earlier works by several people, notably Collie. But the question is, why should you care about these things? Is that blackboard not visible? OK. Well, it's not visible by Sarah, so I won't use it.
It's visible by me, but maybe not.
OK, I'll use this blackboard. So the main theorem about these the history of this is complicated. Essentially, Collie proved a theorem of this kind for one specific example of V and an Euler system, and Rubin kind of took the ideas of the proof and formulated a general theorem. If you have an Euler system and the bottom class, the class over Q, is not 0, and there's a technical condition which is the image of the Galois group in the automorphisms of V, some subgroup of GL2 QP, or in fact of GL2 ZP, has to be large, sorry, GLN rather. And then you get some bound on the cohomology, not of V, but of V star 1. There's a duality game which is indispensable here. So when you have lots of classes in V, it gives you some control on the cohomology of the dual thing. So I don't want to state it precisely. Let me just say that the cohomology is small.
Is this like some sort of irreducibility? I mean, already in your definition, you might want some.
I haven't formulated what I mean by large Galois image, but it's certainly going to imply irreducibility. Right. So what I mean by the cohomology is small is that the strict Selma group, which is a subspace of that cohomology space cut out by local conditions, is actually 0. So for instance, this is a key step in pretty much everything we know towards the Birch-Swinnerton-Dyer conjecture. So what are the examples of Euler systems? Given that they're rather powerful objects, it's legitimate to expect that they should be rather hard to construct. And the list of examples is not that long. The oldest example is the cyclotomic units, where V is the first Tate twist of the trivial representation. So you can get classes in H1 of V by taking the image of units under the Kubo map, and you take the cyclotomic units. So that's a one-dimensional example. A slightly more sophisticated example for a two-dimensional representation is due to Kato. Where you take the representation to be the representation attached to a modular form, and you take this particular dual twist of it. And a more recent example, which I'm going to treat in a little more detail, because its motivation for the new case that I want to introduce later, is the Euler system of valence and Flach elements. So here the representation is four-dimensional. And you take two modular forms, so you get two-dimensional representations, and you tensor them together. So notice that these examples, well, maybe the first one is a little debatable, but certainly these two examples, my representations are representations that are known to be automorphic in some sense, and it's crucial for the construction that you see these representations in the cohomology of some Shimura variety. So all of my cohomology classes are going to come from geometric data. Let's chalk it up. So you find your representation in the Shimura variety, and then you use algebraic cycles, units, geometric things on that variety to cook up cohomology. So I'll explain the valence and Flach case just so you can see in practice what that actually means. So I'm going to explain to you how you construct an Euler system for this representation, the tensor product of the representations for two modular forms. So for simplicity, I'm going to assume that f and g are of weight 2 and the same level. And I'm going to assume that their coefficient field is Q. Just so I don't have to muck around with the coefficients in finite extensions. So I'm going to let y be the modular curve y1 of n, which has a natural model as a variety over Q. So you can take its étale cohomology. So each of f and g crops up in the étale cohomology of y. So by the Kunev formula, the tensor product crops up in the cohomology of y times y. And it's a étale cohomology over q bar. I mean, the variety y times y over q bar with coefficients in qp twist 2. I'm working over q bar, so by the functoriality of étale cohomology, this has the structure of a Galois representation. So I just want to labour that a little bit. And one is maybe mostly used to seeing étale cohomology used in this way as a way of cooking up Galois representations. But there is also étale cohomology for varieties. Erasers are useless. For varieties over Q. And that's what I'm about to use next. I think I should avoid this yellow chalk, it doesn't erase. white chalk, that's better. And these two notions of étale cohomology are related together. So the relation in general takes the form of a spectral sequence. So this is an instance of the Hochschild-Serre spectral sequence. As the E2 term, I have the Galois cohomology of the Galois representation I wrote up there. Étale cohomology over Q bar. Let me not write the coefficients because they're going to be the same on both sides and it doesn't matter much. And this spectral sequence converges to the étale cohomology of the Q variety. The same coefficients. So this is a very general construction, but in this case it actually simplifies rather a lot, because over Q bar this thing doesn't have cohomology in many different degrees. So the H3 is 0, it's an affine surface. And what we get out of that is an edge map. Perhaps I should write that on the next board. So normally this would go to H0 of H3, but that's 0. So we move down into the next layer of the filtration, and we get a map to H1 of H2. And since this is a Galois representation and my V is a direct summand of it, I can just project the FG part and land in H1 QV. Nothing special about Q here. I could have started with Q mu m over here for any m and landed in H1 of Q mu m coefficients in V. So in order to construct elements in the cohomology of V over lots of different fields, I'm going to construct elements in this thing, absolute étale cohomology, of Y over many different fields, satisfying norm relations. And suddenly I have more tools available. I have more geometric things I can do because it's cohomology of a variety. Oh, sorry, that is exactly what I didn't want to write. I hope that's still legible. That's Q mu m in the subscript and for Q in QP2 for all m. So because the question is now one about étale cohomology of varieties, and étale cohomology is a nice theory, you have push forward and pull back maps along embeddings of varieties, there are many more things you can do. you can take the diagonal embedding of y into y times y, and you can push forward cohomology from y to y times y. And you can build cohomology on y fairly straightforwardly. So if you take the space of regular functions with no poles and no zeros on y, so these are classically modular units, there's a map from there, the common map for a Tal cohomology, going into h1 of y, the coefficients in QP1. It's perhaps most familiar to see this landing in h1 of fields, but you can do this with h1 of more general varieties. And then there's a push forward map, iota lower star. And because y has codimension 1, it bumps up the twist by 1 and the cohomology degree by twice that. So the cohomology degree goes up to h3. This is over Q, of course. Tal cohomology. Landing in QP2, which is exactly what we wanted to do for m equals 1. So in here there's a special element, I'll call it Gn, the Siegel unit. And it maps all the way over here to something which I'll call the valence and Flach element for m equals 1. So this has been studied by an awful lot of people. I've mentioned Valenson and Flach. Harris and Scholl have studied these guys, and more recently Bertolini, Darmon, Rocha, and probably some other people I've missed out. So the natural question is, how does one extend this to an Euler system? A theorem due to Antonio Ley, myself, and Sarah Zerbes from a while back now, 2014. There are elements BFM for all m greater than or equal to 1. Extending this, and satisfying the Euler system norm compatibility relations. So I'll give a brief hint as to how they're constructed. You replace this diagonal embedding with something more sophisticated. So I'm going to map a larger level modular curve into the product of these two modular curves of level n. And in terms of points on the upper half plane, this map is given by Tor goes to Tor and Tor plus 1 over m. So it's a fun little exercise to check that that's actually well defined on this quotient. This is essentially the same statement as saying that when you twist a modular form by a character of a Dirichlet character mod n, m, its level goes up by at worst m squared. And we take Bfm to be iota m lower star composed with kappa p of the Siegel unit on this guy. And the important point is that although these are both varieties defined over Q, iota m is not a morphism of Q varieties. Iota m is only defined over the field extension Q zeta m. So we have a chance of getting things that are interestingly defined over these higher fields. And the hard part is proving that you have some norm relations for these once you project into the FG isotypical part. So the original proof of that, I wouldn't wish it on anybody to read it. It was something like 20 pages of extremely dense and rather nasty calculations of double cosets and orbits and cycles. And it's kind of clear that if you're going to extend it, then you need some new ideas. And that's what we'll see later in this talk. So what I want to talk about today is a new Euler system. The Euler system of what we call lemma-Flach elements. Associated to GSP4 automorphic forms. So I'm going to take F to be a Siegel modular eigenform. Just for simplicity, I'm going to take the weight to be the smallest cohomological weight, so weight 3, 3, but actually any cohomological weight is OK, but I just want to describe it in the simplest case. What this doesn't cover is the non-cohomological weights that we heard so much about in the talks by Vincent and George yesterday morning. But
just a question. What are the consequences you get about like DSD time conjecture with your Euler system?
Well, there's another ingredient which you need. Nothing I've said here guarantees that the Euler system is not the zero Euler system. But that theorem, together with the explicit reciprocity law proved in various versions by Bertolini, Dalman, Rothschild, and by myself, Guido Kings, and Sarah, if you put those together, then you get the Bloch-Kato conjecture for Rankin-Selberg convolutions in the critical range. Well, you get the rank 0 cases of. And yes, and the usual consequences for finiteness of Selma groups and Char and so on. I didn't want to go into the arithmetic consequences, but there certainly are some. So I've chosen my Siegel eigenform. So attached to it, there's a Galois representation. If Vf is the usual cohomological thing, I actually want to take Vf star. And because I'm in this minimal weight situation, the Hodge-Tate weights are 0, 1, 2, and 3. And just to completely avoid discrepancies, for me, the Hodge-Tate weight of the cyclotomic character is 1, although I think there are many people who feel it should be -1. I believe I stand with Fontaine there. So I'm going to assume F is what we call non-endoscopic. So it really belongs on GSP4. It's not lifted from GL2 or GL2 times GL2. And this implies that VF is irreducible. So the kind of things I'm ruling out by this are things like Saito Kurokawa lifts from GL2 times GL1. So by results of a lot of people, Taylor, Weissauer, and some others, this guy appears in a Shimura variety, and it's a Shimura variety, of course, for GSP4. So I have some variety S, and I take S over Q bar with coefficients this time in QP3. And S is a Siegel modular threefold of some appropriate level. So again, we want to build cohomology classes in this cohomology group over different cyclotomic fields. So the strategy, and this is due to Francesco Lemma, you start with the observation there's a nice subgroup that you understand inside GSP4. And it's almost the product of two GL2s, but not quite. You need to take the fiber product over GL1, so pairs of matrices with the same determinant. So from this inclusion of groups, you get subvarieties of your Shimura variety. And if your levels are chosen nice enough, what you're seeing is the product of two modular curves embedding as a subvariety of S. And let me call this embedding iota, because this is going to play the same role as the diagonal embedding in the theory of variance and Flach elements. Wrong page of my notes here. So the next step is you take two Siegel units, one on each factor of y times y, so you can regard these as two independent rational functions on the product y times y. And you take the cup product of these two things. So this is the exterior cup product of two cohomology classes on Y. And each one of these lives in H1 twist 1, so the product is in H2 twist 2. And then we're going to define the first lemma-Flach element to be iota lower star of this guy. And where are we landing? Again, iota has codimension 1, so this goes up by 2, and this goes up by 1. And we're in precisely the space that we want to be in, because this is going to map to H1 of V. Sorry, that should have been S. Thanks to whoever shouted that out. It's S over Q. And that maps to H1 of QV. So exactly as with valence and Flach elements, this raises several natural questions, some of which we can answer and some of which we can't. The most natural question is this guy non-zero? And we can't answer that question. But what we can say is that it extends to an Euler system. And this is the main result of a recent preprint of myself with Chris Skinner and with Sarah. It was put on the archive earlier this year. There's an Euler system of elements LFM defined over the nth cyclotomic field, extending this LF1 that I've just sketched the definition of. At present, we don't have a universal criterion for that. It's in individual examples for a specific f, there are numerical invariants you can compute that would prove that for that example it's non-zero. But we can't relate this to values of L functions at present.
Well, one should maybe say that in fact...
Can we discuss this after the talk? I want to go on describing some things we do know. So just to construct these elements, the idea is actually very similar to the construction of the valence and Flach elements. You take your embedding iota and you replace it with something slightly more complicated. You kind of perturb iota to get something that's defined over a field extension. And what you do in both cases is you take the naive embedding and you translate it by a sufficiently generically chosen unipotent element of your group. In this case, you take the element of GSP4 that looks like this. You put 1 over m's in the above diagonal places that aren't hit by the subgroup H. Right?
Good question. When you say take two Siegel units, is that G and F? I'm just confused why there's G in this.
There's a single Siegel unit on Y, but you regard it as a unit on Y times Y by pullback along the two projections.
Okay.
So you then get, and the point is this is not trivially zero. If you take the cut product of two copies of kappa p of the same unit on the same variety, then you get zero.
Oh, that's why you, okay.
So the pullback of this to the diagonally embedded copy of Y is zero.
So it's like GY1 and GY2.
It's kind of kappa p of pi 1 upper star of G, kappa p of pi 2 upper star of G. Maybe I should write that. So now pi 1 and pi 2 are the projections of Y times Y onto the factors. And that's what this is defined to mean.
So there's some integral representation L function matching with this picture.
Exactly, and this is
Factors.
this.
Two L functions. Which L function?
There's a two-parameter integral here, which gives you the product of two different shifts of the spin L function of f. But it is the spin L function underlying all of this. Yeah, so we take this naive embedding, the obvious embedding of H of our small group into GSP4, and we translate it by this element, and then project it into the quotient we work with. So this gives you something defined over Q zeta m as before. And exactly the hard part is to prove the norm relations. And it was clear that doing this just by hand, by carefully keeping track of all of the different components of the images of cycles that come up and grouping things together in a clever way, was just going to be impossibly painful. It was painful enough for GL2 times GL2, and here it was going to be vastly more painful and clearly not doable. So a new idea was needed. And that brings me on to the last and possibly most important section of this talk. Norm relations and multiplicity 1 theorems. And the idea is to replace the very difficult problem of proving norm relations for these elements with a much, much easier problem in local representation theory by using some clever results about multiplicity 1 for decompositions of representations. So let me explain this in a simple case. So I want to show that the co-restriction of the element for m equals L is appropriate Euler factor times the element for m equals 1. And here L is a good prime, which means it doesn't divide the level of the Siegel modular threefold on which all of this is taking place. There's nothing intrinsically more mysterious about the case of general M, but the notation is much nastier. So we're going to organize our construction in a certain way that enables us to use representation theoretic ideas. It's supposed to be a curly Gothic Z, by linear form Z going from some explicit representation of h of the finite at L's. Sorry, I forgot to define my notation here. I'm just going to put G to be GSP4, and H is going to be this subgroup embedding inside G. So here I have some explicit representation of H, which is the one generated by the translates of the Siegel units. And here I have the automorphic representation coming from F. And there's a bilinear pairing between this and this going into H1 of Q comma V. So there's nothing particularly mysterious about this. A vector in here is some linear combination of Siegel units. A vector in here is some linear combination of translates of the new vector. And I send that to the appropriate linear combination of translates of the push forward of my Siegel unit. And this gives me a way of building classes. So firstly, the point is that both of the things I'm trying to compare are values of Z on explicit test data. Let's say x tensor y and x prime tensor y prime respectively. And the point is that these are identical away from the prime L. So x is the spherical vector, well, sorry, it's the new vector everywhere, as is y, and this is something slightly more complicated at L, but it's the simplest possible vector at all of the upper primes. And we want to compare those. And the other key point is that this Z has an equivariance property. Essentially, if you take some cohomology class on the Shimura variety for H, you can either translate it on H and push it forward, or you can push it forward and translate it. And if you're translating by something in H, those things agree. So what that translates to is that Z of H x hy equals Z of xy. So the key input from representation theory that is going to make all of this work is the following theorem. This is quite an old theorem due to 3 Japanese mathematicians. This is not the same Kato as in Kato's Euler system. It's a different Kato. It's not the log geometry Kato either. So if sigma and tau are unramified principal series representations of H of QL and G of QL respectively, let me make sure I've written this the right way around. Then the H invariant linear functionals on the tensor product of sigma and tau this is just going into the trivial representation of H, that has dimension at most 1. So I'm going to take this to be some product of tau L's, and this is some product of sigma L's. And I want to compare two values of a bilinear form on tau L tensor sigma L. Be a bit more consistent with my notations. So we have some bilinear pairing in this space coming from this monstrously complicated global construction, which we don't really understand at all. But if we can build anything else in this space, then the global one must be a multiple of it. if we can find a non-zero z hat, which is in this space, some purely local arbitrary linear functional, bilinear form, which has the right H equivariance property, and we can prove that our elements do the right thing under this new bilinear pairing, then they must have done the right thing under the complicated global one as well. So if we can show that z hat of xl tensor yl if we can show that this equation is satisfied for z hat, then it implies that this vector xl tensor yl minus pl of 1 times this guy, this is, if we think of the projection of that to the H coinvariance, and that space of H coinvariance is dual to this, so it has dimension at most 1. So it follows that we must have that this relation holds for every bilinear form z hat. And in particular for the global one we started with, sorry, I've forgotten my PL of 1 factor. So we've taken some question about a terribly complicated cohomological bilinear pairing, and we've shown it to be equivalent to a question about some arbitrary bilinear pairing that we can cook up at will. So there is an explicit z hat coming from zeta integrals and then this relation star is a moderately easy exercise. And by this multiplicity 1 machine, you get the desired relation for the much more complicated bilinear form we wanted to study. So I maybe have time to just make 1 or 2 remarks on that. Yes, it's an integral representation for the local spin L factor using the Bessel model. But the important thing is that it expands to a bilinear pairing with this equivariance property.
And it's always non-zero?
And you evaluate it on the spherical vector and it's non-zero.
So this space is always one-dimensional?
It's one-dimensional subject to a condition on the central characters. So that is something I was about to mention. So the first remark is you don't actually need to know what PL looks like, what the local L factor is, for this calculation to work. You know that zeta integrals produce L factors, that's what they're for. There is an expression for PL of x as of its coefficients of various linear combinations of Hecker eigenvalues, but it's rather complicated. And this argument allows you to prove the norm relation without having to know what those coefficients actually are. In sharp contrast to the brute force argument we used in the Rankin-Selberg case, where we really had to know all of the coefficients of the of the L factor as Hecker eigenvalues, and you look at the actions of those Hecker operators on our units. The second remark is that this works whenever you have suitable multiplicity 1 results for local representations. And although it's slightly disguised by the way I've written it, this is just one instance of a general theorem. We have PGSP4 isomorphic to the split form of SO5, and H modulo the centre of G, which is actually slightly smaller than the centre of H, is, so the image of H in this quotient is SO4. So you can see Kato-Murase-Sugano as a statement about restrictions of representations from SO5 to SO4. And the general problem of restricting from SON plus 1 to SON has been studied. This is one aspect of the Gann-Gross-Prasad conjectures. But of course, this is for spherical representations where these conjectures are known. And this is just the n equals 4 case. And if you look at the n equals 3 case, you get a new proof of the Beilinson-Flach element norm relations. So this is being worked out by one of Sarah's PhD students, Giada Grossi. But there is also Gann-Gross-Prasad for other kinds of groups. Rather than looking at orthogonal groups, you can look at unitary groups. So if you take representations of a unitary group of degree n plus 1 and restrict it to the subgroup un, then you also have these kinds of multiplicity 1 results. And work in progress by myself, Chris Skinner, and Sarah, we're going to use this to construct an Euler system for U21. More accurately, GU21. Sorry?
It's nearly finished.
Yes, this is in progress.
But again, the big flats will come from the Siegel unit. Right, push forward from up.
Exactly. You're looking at embedding some class coming from GU11, and GU11 up to messing around with the center, it's basically GL2. So you're pushing forward, in this case, just one Siegel unit into a Picard modular surface. And there are various extensions of this. For example, there's something you can do for GSP6. We're discussing with Shrenik Shah about whether we can make something work for U22. And there seems to be quite a few examples of Shimura varieties of moderately small dimension where you can use these kinds of ideas to build Euler systems, and where you can use multiplicity 1 results to prove the norm relations with very little work. So thank you for listening. I think I'll stop there.